So it is now clear that the optical waveguide is the basic building block for photonic integrated circuits, right? So we say integrated optoelectronic devices and circuits, and nowadays actually in literatures and scientific community, it is together called like a photonic integrated circuits. So sometimes we'll be just calling simply photonic integrated circuits. That includes your waveguides and components, devices, and circuits together. So photonic integrated circuit. Now, so if it is clear now to you that optical waveguide is the basic building block, we must understand a bit clearly the working principle of optical waveguide. Okay, so for this optical waveguide understanding will be more clear, as I said before, if you know a bit of electromagnetic theory, especially Maxwell's equations. So I hope you have gone through all those things, but just for completeness, I will just quickly go through the Maxwell's equation and how the Maxwell's equation is used for designing optical waveguide and different type of components. Okay, so in the outset, I must tell that the optical waveguide, you will have various configurations, various geometry optical waveguides are there. For example, there are, if I just classify them, one is called diffusion doped channel waveguide. Diffusion doped channel waveguide. Of course, I will not discuss about the optical fiber. That is also optical waveguide. But what we are talking about, photonic integrated circuit. So it is in planar waveguide circuit. That is what I mean to say. So diffusion doped channel waveguide. So one example I can say that it is maybe either you take a glass substrate. So this can be a glass substrate, and or some other material. It can be polymer, it can be some crystal, that can be artificial synthetic crystal or whatever. For example, I just consider very popular lithium niobate. Lithium niobate, LiNbO3, lithium niobate. Okay, so this two substrate I can think of if I just talk about diffusion doped channel waveguide. How it is done? You take a glass. You know, glass refractive index is around 1.45. At so refractive index here, this one you can consider around 1.45 at lambda equal to say 1.55 micrometer. Similarly, lithium niobate, if you just see, it is a birefringence material. Two types of refractive index is considered. One is around 2.12 and another is called 2.21. So that depends on, because it is a crystal, any electromagnetic wave propagates inside the crystal, you have to check which direction is polarization. So depending on the polarization means electric field oscillating in which direction. So depending on that, it will experience refractive index. One is called ordinary refractive index, that is actually O, and another is called extraordinary refractive index. So that depends on what is the cut of the crystal. Okay, but I think never mind, that is around 2. Refractive index you can consider around 2. So this is your wavelength. And for diffusion doped, you know, you need a core and cladding for any waveguide structure. So in glass, normally what it is done, just in the surface layer, you just pattern and selectively you dope some with some additional material. And normally it is done with some kind of metal. That can be some kind of aluminum, that can be any other methods, any other metal. If you just somehow you can incorporate in the surface layer selectively to define a core of the cross section, that region actually, because of the presence of foreign material, you can see some change of refractive index. But you have to be careful that that refractive index should increase. So one method is actually just incorporation of H plus, silver atom incorporation. So there are some methods you can actually incorporate silver atoms in the surface by chemical diffusion process. Then you can have some kind of aluminum, it is silver Ag, right? Can go inside and you can define your core. So depending on that, depending on your refractive index change, you can design how much dimension of the core will be to support at least how many modes you want to allow. So that will come to that point. So ultimately, at this point of time, you just try to understand that for any waveguide, you need a core and you need a cladding. And core region should be higher refractive index, and substrate here is glass. Glass should be a little bit lower refractive index, and top layer, effectively you can consider some air. Air itself is a cladding layer, but if you want to just cap it with some other material, that should be lower than the refractive index of the core. Then it will be a channel waveguide, or sometimes it is called buried channel waveguide. It's buried inside the substrate. And in case of lithium niobate, its most popular is you can diffusion dope. You just deposit some stripe of metal. It's the most popular is titanium. Okay, titanium layer you deposit, well-defined layer, maybe 100 nanometer or so. Then you put this deposited titanium, this lithium niobate pattern with titanium stripe in a furnace. You raise the temperature up to more than 1000 degrees Celsius. Then what happens? This titanium can go inside, can diffuse inside, and once it diffuses inside, you can get some kind of graded index, refractive index change. Just remove this one. So you will be getting something like this. So this type of profile you will see, titanium profile. That means inside lithium niobate, normally titanium is incorporated in the form of titanium 4+ ions. So when these titanium atoms are incorporated selectively in a selected region, so depending on the titanium concentration profile, you see the refractive index change. So that refractive index change can be treated as a core. And lithium niobate, that should be higher than whatever the refractive index here. And lithium niobate substrate can be a lower cladding, and upper cladding will be air. Or again, you can put some cap material, some cladding material here that should be lower than the refractive index of the core. That is actually titanium, or sometimes it is also used by proton exchange method. Proton exchange means, you see, lithium niobate. So lithium ion can be replaced, substituted by proton, means H+. So it is possible if you pattern, selectively open the window, and then if you insert that submerge this substrate into a weak acid, something like benzoic acid, then some kind of ion exchange takes place and H+ will go inside. That is called proton, so-called proton exchange method. Anyone having question?
Sir, you are trying to increase the refractive index for optical confinement now?
Yeah, I want for optical confinement, right?
Yes.
Yeah. So that is actually H+ or titanium can be incorporated. So that is what called diffusion dope channel waveguide. And this lithium niobate, as you know, this is very popular for integrated optical modulator, high-speed modulator. We'll discuss later. And glass substrate, if you do some change, normally you can only design some kind of passive devices. Active device, that means you cannot control from external electric field to change the refractive index. Only passive waveguide, for example, power splitter, and maybe some kind of filter, resonator, everything you can do, but not, it's kind of limited applications. Normally glass substrate is used. Lithium niobate is well known for modulator and commercialized. Whatever high-speed modulator you get in the market, they are actually lithium niobate modulator. Fine. That is actually based on channel waveguide structure. Nowadays also they are trying a little bit different type of configuration. I will discuss that later.
Sir,
Yes.
as the refractive difference increases between the core and the cladding, does the confinement increase? Optical confinement.
Yes. So it depends. Optical confinement means tightness of the guided mode, right? You mean to say how tightly it is confined. That
Yes.
depends on the refractive index of the core, refractive index contrast between core and cladding. So higher the refractive index contrast between core and cladding, so you can design your waveguide cross section smaller, so that mode field can be tightly confined. That's possible. Yeah, true.
So, what is the lowest limit that what is the lowest difference? Sorry, the highest difference that we can go?
Refractive
Oh,
index.
yeah,
Yeah,
the refractive index. What is the highest difference
actually,
we
you
can?
see, in theory, the refractive index can be as high as possible. If you find a material and if you find a way out, that refractive index can be, as long as your electromagnetic wave or light wave is transparent, of course. It should not be heavily lost. So refractive index can be as high as possible. But we are limited by the availability of the material and technology. Okay. So normally when we talk about silicon photonics, for example, their actually refractive index for 1.55 micrometer, the refractive index is in the order of 3.46. So if your cladding is air, then you can imagine refractive index contrast is, air refractive index is 1. So refractive index contrast is 2.45. So, and also gallium arsenide 3.5 semiconductors, if you see, their refractive index is also in the order of 3.5. So those are the material normally. Indium phosphide, it's very popular for some of the optical components, integrated optical components. Their also refractive index is close to 3.5. So those are the highest possible refractive index we can consider as a core for optical design, optical waveguide design. And if you go for, if you have some material, if you find or you synthesize maybe some material which is having refractive index probably 5, 6, 7, so most welcome. So that is, I think, so far to my knowledge, I think this silicon and gallium arsenide or indium phosphide is the highest possible refractive index available for waveguide design. Is that clear?
Okay. Yes.
Yeah. Okay. So diffusion doped channel waveguide, and another type of waveguide we are calling as a some kind of Reeb waveguide structure. Reeb, and sometimes people confuse also with a ridge structure, RIDGE, ridge waveguide structure. So this actually depends on your technology and materials availability. You can actually design different type of waveguide geometry, waveguide core, I mean to say. For example, this Reeb and ridge waveguide structure, as I said, that you have a substrate, any substrate that can be glass, that can be any other material, for example, semiconductor conducting material like silicon, like gallium arsenide or indium phosphide, whatever material, that is substrate you use for your handling wafer. So that is we call as a substrate. And that is no way it is being used for your waveguide design. It is just for handling purpose, for your fabrication, etc. carrier. It's called handling wafer sometimes, substrate. And then what you do, you somehow, if your technology supports, you can deposit a material on the top of it with good quality. That should be transparent, no defects, nothing, as small as possible defects things. So if this is a material of having some kind of refractive index lower, maybe you can refractive index, you can consider something like that, N1, right? N1 refractive index, right? And then you can have another material on the top of it having refractive index N2. Okay, and then this this N1 material, that should be considered as a lower cladding. Lower cladding. And then this one, this layer, we will be using as a core material, right? And then on the top, you can have another material if you want. Otherwise, you leave it as it is. It can be air. That can be considered refractive index N3. You can consider upper cladding. I hope you can read whatever I am writing, right? Okay, this is upper cladding. So these three different material system, whenever you are just depositing one after another, you should be careful that this N2 should be greater than N1 and N3, because N2 is the core. N1 can be equal to N3 and it can be also not equal to N3. Both can be possible. Okay, just simply if you maintain this condition and you maintain this condition, then this system you can call it as a planar symmetric waveguide. Planar symmetric means you have a planar core that is stretched in 2 dimensions. If it is consider this is a y and this is a x axis, right? So then this planar structure you are thinking about in the yz plane. Okay, x is the vertical direction. And you can imagine that, okay, this is a coordinate, you can consider this is 0, and say this is maybe some thickness you can consider. Say you can consider this thickness probably maybe d in the x direction. So its coordinate is 0 and then d. That means 0 to d you can consider as a core material, which you can imagine that is stretched in a yz plane. Okay, and if N1 equal to N3, then it can be symmetric planar waveguide. For example, if this core material is, for example, SOI, silicon on insulator, and this is suppose silicon. For example, I am just giving one example, and this is silicon on insulator, and this material is SiO2, right? SiO2 means silicon dioxide. And then top material is also you are depositing some kind of silicon oxide. That is possible in CMOS industry, SiO2. And this material is your SOI. So-called SOI, it is basically thin layer of silicon. So then this layer itself, it can be useful as a planar waveguide structure. For example, you can launch a light here in this core region. It can be confined vertically because of the upper cladding and lower cladding. But it is allowed to propagate in both direction. That means in the y direction as well as z direction. So all 2-dimensional propagation is possible. Light can be diffracted or diverge in the yz plane. Okay. So this is a planar waveguide. If some applications are there also, you can use this planar type of structures. Okay. And fortunately, this type of materials, the silicon on insulator substrate, that means without oxide, that they are actually nowadays available commercially, good quality. So wafers are available commercially, both in electronics industry, both for electronics industry as well as photonics industry. Okay, optical grade also available. You can get up to SOI wafer up to 18-inch today, 18-inch wafer diameter, 18-inch wafer. And but foundry, so far I know that they are using up to 12-inch wafer, and most of the photonics foundry, they are using 8-inch wafer. But some, I think TSMC, TSMC in Taiwan, they are using 12-inch wafer, and other foundries normally they are restricted with 8-inch wafers. All right. So this is something very popular these days for photonic integrated circuit. This is the wafer you can buy. Normally, it is available in the market, but it is a monopoly. Only one company manufacturing this good quality SOI wafer for photonics industry. But for electronics industry, there are multiple companies are available. For photonics, you need a little bit of high quality this SOI layer. So only Soitec, it's a French-based company. They are producing and they are supplying whole world. Okay, this thing. And I think we bought this 8-inch wafer very recently, but it's a couple of years ago. I think each wafer costing about I think $700 US dollar, something like that. That's big expensive compared to your silicon wafer. Okay, so this is a planar, but this is not called your waveguide or ridge waveguide structure. Okay, so how you can get your ridge waveguide structure? Because you want something called confinement also in the y direction. Two-dimensional confinement required. So what it is done, you have your wafer, that is the we are just showing the portion of your wafer, that is substrate, handling wafer, it can be silicon, and then you have your box. It is actually called lower cladding, and but technically it is called box. Silicon substrate, and this is box. That means buried oxide, basically silicon dioxide. And then whatever you have your material layer, that is actually so-called SOI. This is the SOI layer. Okay, this substrate you are getting from the market, and you know that this SOI itself is a planar waveguide. But what you could do, on the top you can put another oxide, that is called top oxide layer. If you want to get symmetric waveguide, that is TOX. But what you do some kind of selective lithography process, so that you can actually create two-dimensional confinement. Okay, so let us just think like this. And what you could do, you can just define selectively, maybe some region you selectively you remove, this region and this region you selectively remove, so that you are getting something like this. Okay, maybe I can try it like this. I can add later. So you can get something like this. So this region you have higher height, this region, okay, higher height. So this is the region, and this region little bit lower height, and this is little bit lower height. So selectively you are removing this region bit. Suppose if this is say about, typically we have 220 nanometer, and if you just remove, maybe just depends on your how much your width you are using, say maybe 50 nanometer, 60 nanometer, 100 nanometer, or maybe you can completely remove this region. Then this region actually can be useful for your, if you are just removing complete thing, you can just think like this.
Sir, what is this 220 nanometer? The width of the SOI layer? The 220 nanometer is the width of the SOI layer?
Thickness. We don't say width. That is the thickness.
Oh.
Okay. So SOI, that means silicon or insulator. Okay. So this is your silicon layer. This is your silicon layer. But selectively you are removing. So you are just trying to, this region will be extended this side, this region will be extended this side. You are just removing this area. So what happens? This is something like that rectangular cross section of silicon. And bottom layer is oxide. Top layer is now air. But you can just fill complete layer with oxide. Then you can have something like this. And if necessary, as I said, that you can have some layer of silicon you can leave. Okay, maybe I can just put a little bit differently so that it can be easier. Yeah. So this is your silicon layer you are leaving. This is your silicon layer, and this region may be your top oxide layer or ER, whatever. Then this can be considered as a core waveguide, and this is called rib or ridge waveguide structure. And whenever you are removing completely, then it is just rectangular cross section. It can be rectangular, it can be square or whatever, depending on your design, etc. You can consider, but because it is a silicon and refractive index is 3.45 or so for 1550 nanometer, you can design this cross section in the order of submicron, in the nanometer scale. So 220 nanometer height, and horizontal direction of also you can consider 400 nanometer or 500 nanometer, then that is sufficient to confine a light inside the silicon, and that can be considered as a core of a waveguide. Okay, that is called rib waveguide. And if you are completely removing, then it is called photonic wire waveguide. This is photonic wire. Wire means, you know, it's kind of it is borrowed from your quantum technology. Because quantum technology, you know, if it is one-dimensional confinement of electron, then it is called quantum wire. And if it is two-dimensional confinement of electron, it is called wire. Just any electron can propagate with two-dimensional confinement. Only one direction it is allowed to propagate electron in a conductor, for example. And quantum wire, different type of application, that is called quantum wire. And if it is three-dimensional confinement, then it is called quantum dot. Quantum dot. And is there any advantage of not removing the entire? Yeah. So that is a good question. I think Parth is asking that. I think better whenever, because I may miss whatever you are posting in the chat box. Better you can unmute. You can ask question directly so that I don't miss your question. So yeah, his question is that, is there any advantage if you leave a little bit of silicon layer? Yes, there are some advantages. We'll come to that point. Whenever you need some kind of, probably you can just recollect whatever I have presented earlier, that we leave some kind of slab region here so that you can dope p-type and n-type if it is silicon, so that you can create also pin type diode structure, and that type of structure normally used to design modulator. Okay, so whenever you don't need that type of application, that type of modulator application, only passive waveguide structure, or maybe thermo-optically tunable things, then you can use just without this slab region. But what I was trying to mention that quantum dot. In case of waveguide case, if it is photon or light is confined in three direction, then it is called resonator. Okay, waveguide resonator, you know, in microwaves, you know that three-dimensional confinement square box you can consider as a resonator. So here, since photon is allowed to confine in a small region, and that is to submicron cross section, that's why it is called photonic wire. It is not quantum wire, it is a photonic wire. Photon within the something like quantum wire, that is photonic wire. So you should not misjudge. That is basically optical waveguide, but with small cross section. Okay, so this is one example of rib and ridge waveguide structure. So today's technology, I think normally these two types of waveguides are popular. There are some other types of waveguide, different type of cross section depending on the technology, but they are not so popular. So we will not discuss that thing. Okay. So any questions till now?
Sir,
so that is,
hello, sir. Hello. Sir, you remove the silicon on left and right side. Okay. So because of that, refractive index of middle one is higher compared to other both side. That's why it's confinement now. That's the reason.
Right.
Sir, I want to ask one question. How the refractive index is depend on height? Means how the if height is more, then refractive index is more, and if height is less,
yeah,
that is
the subject we want to discuss in future classes. But normally, as I qualitatively says that it depends on depending on the height, you can actually use your effective medium theory to calculate average refractive index in this region, average refractive index in this region, average refractive index in this region. And whenever you are calculating your average refractive index, that time you should use height as a weightage. So that weightage contributes to different type of effective index. Okay, that is qualitatively, if you ask me, I can answer that way. Otherwise, we'll be just learning how that is coming into picture. Okay.
Okay, sir. Thank you.
Right. Any other question? If not, I proceed. So now we need to know, next thing what we need to know how, for example, we are talking about 220 nanometer. We need to learn, is that 220 nanometer is sufficient? Why not 100 nanometer? Why not 50 nanometer? Why not 300 nanometer? Why not 500? Why not 5 micron? Normally available also, so you refer. Why we are using that? But one point is clear, that smaller is better, because you can scale it down. You can integrate more number of components. So smaller is always better. But we'll find that it's a much smaller is not always good. Sometimes smaller core size, it can give you a more solution, but more diameter will not confine within the core. It will extend because of evanescent field stretching. So those are the questions we need to understand now. That how to design a waveguide for a given technology. I have a technology to get this type of structure, and I know that my technology limitation is that I can go down to, say, for example, 100 nanometer technology, 100 nanometer dimension feature size I can fabricate easily. So I know that is our limitation. I cannot define structure maybe less than 100 nanometer for a given technology. But today, you know that because of the advancement of nanotechnology, etc., particularly CMOS industry, they can go down to sub 10 nanometer technology you can do. But for designing an optical waveguide, you have to keep in mind that your waveguide cross section or dimension, feature size dimension can be smaller, but ultimately you rely on optical waveguide for your device design, for your circuit design, and that optical waveguide you need longer things, longer length. But as the cross section you maintain for longer length, it is actually you can say that your light will be confined and you can just bring your light anywhere. But there is a fundamental difference of normally quantum wire or wire transmission line you use in integrated circuit, electronic circuit, and optical waveguide you use in your optical photonics integrated circuit. What is that? You know, normally smaller the dimension for electronics, for transmission line, we understood that there is a resistance can be increased. Resistive loss will be there, capacitance, fringing capacitance, all those are the additional problem. And resistance increase means what you are encountering there, you are encountering smaller cross section, so electrons are not getting enough area to move in. So not many electrons can move, so that way your conductivity, total conductance is actually reduced, so resistance increased. So that is the way out. But your surface layer actually that is also contributes to the resistance. Smoother the surface, your electron can can be transported without any scattering. Without any scattering means your resistance will be lower. That is one problem. But in photonics also, you have to see that your photons or electromagnetic wave should not have kind of that type of resistance, or like resistance means R-type resistance, which actually contributes to your loss, heating loss. But here, electromagnetic wave, if it is transparent to material medium, you can ensure that probably no heating loss is there. So energy will not be lost due to heat generation. That is for sure. But one more thing you have to keep in mind, that if surface is not smooth enough, okay, then you can encounter with a scattering loss. So loss of the waveguide will increase if surface is not smooth. Suppose your waveguide dimension is in the order of some 500 nanometer. Okay, and what is the wavelength? 1550 nanometer, right? You are talking about communication band 1550 nanometer. And because of the higher refractive index, that 1550 nanometer you can get effectively a more solution. But since wavelength is higher, suppose your roughness or waveguide dimensional variations is there. As you see the cross section along the length, if it is varying because of the some kind of roughness, that is actually you cannot remove through your, you cannot get very perfectly using your technology, then that encounter a loss. So you need a very smooth roughness. And dimension also, if it is changing suddenly, suppose one particular cross section is there, suddenly dimension changed. So what you know that sudden dimension change means effective index is changed. So you know that as if electromagnetic wave is propagating from one medium to another medium. When refractive index is different, you can consider two different medium. So at the junction of these two medium or the two dimension, you can encounter Fresnel reflection loss. So those type of things you have to consider. Is that clear?
Yes, sir. Yes, sir.
So those are the technological limitations. So you need to know that what is the minimum dimension you can design, not only considering technology, but also you have to consider the mode size, confinement, tightness, all those type of things you have to consider. So that is why it is a very challenging task to maintain the cross section throughout the waveguide length, and which is less problem for your electronic wire transmission line. So there somehow you can manage, you can actually sharply bend electrical wire, but waveguide you cannot bend sharply. There you will see that some way of scattering losses, leaking of light. So those are the limitations there. And as a photonics engineer, if you want to design a device, etc., you need to know all these. How small you can design, how tightly you can bend your waveguide structure, because bending is very essential for designing your waveguide. Okay, so all this actually very, very important to understand. And to understand all these, we cannot avoid Maxwell's equation. We need to know the basics of Maxwell's equation. That's why again and again I am insisting, go back and read origin of Maxwell's equation, plane wave, all those type of things if you have not learned so. But for completeness, I will just give a recap here. I think this recap maybe today and one more class needed or something like that to understand the design of basics of optical waveguide. And from there we will build up our theory of waveguide and coupled mode theory, all those type of things. Any question? No. So recap, if you see, I hope you know the four Maxwell's equation. What are those? I think Karloff E is what? Electric field plus so how many of you know this equation? I hope all, right?
Yes, sir.
Okay. So this is your Karl equation. That means actually, popularly, this this is first law, one of the equation of Maxwell's, but originally it is known as, what is that?
Faraday's law.
Yeah, it's a Faraday law. And then another equation, Karl equation, you know that, Karloff H equal to what is that?
JC plus JD.
JC plus JD. So we can just put down the thing that is better to write. Karloff H equal to, this is Karloff equal to minus del B del T, and this one equal to so-called JC means conducting current density, right?
Yes, sir.
That is actually sigma E. Conducting current is, sigma is the conductance, basically current density we are writing. Conducting current density, and plus what we write?
dt by dt.
Displacement current.
Yeah, dt by dt.
Del D del T. So this we write as a 1B. I think all of you know this. And then two more. This is actually called Ampere's circuital law. Ampere's law, right? And then divergence of d equal to rho V. Let us consider this one as 1C. and then you have your divergence of P, B. That is actually 0 in principle. This is actually we define as 1D. So these are the four Maxwell's equations, and I hope you know what is the unit of E. Anyone?
Ampere per meter. Ampere per meter, sir. Ampere per meter.
Ampere per meter, right? Electric field is ampere per meter. Is that? Are you sure?
Volt per meter.
Yes.
Oh, sorry, sir. Volt per meter. Yes, sir. Sorry, sir.
Volts per meter. And then H is your amperes per meter.
Yeah.
Right? And what about T?
T equal to
displacement vector. What is the dimension of D?
Volt per meter squared होगा ना?
Really? Anyone?
Volt per meter only.
Volt per meter.
Volt.
That is E.
Squared, I think.
So you mean to say dimension of E and D are same?
Coulomb per meter square.
Yes, sir.
Squared.
Yes.
Squared.
Coulomb per meter square. And what about B?
Henry per meter.
So you know, if you have a monopole, a magnetic pole, Coulomb is charge unit, right?
Yeah.
And here we consider Weber per meter square.
Mm.
Yeah. And what about rho V?
Coulomb per meter cube.
Yes. SI unit Coulomb per meter cube. And anything else? Normally, this one you consider so-called JC, and this one you consider as JD, right? Displacement current. And their dimensions are ampere per meter square. Is that correct?
Mm.
Okay.
Yes.
So you can relate that how dimensionally correct also both sides. You can try to relate also. This is all about, you see, this is divergence, you will be getting a scalar quantity. Divergence, it is a scalar quantity 0. So this side is a vector and that side also has to be vector, and dimensionally should be correct. And this is also same thing you are considering. So these are actually known as Gauss Theorem. Okay. So Gauss Theorem, all these are from the school level, we learned that thing. And along with this, we need to use a couple of material properties, that material relation, how this displacement vector, this magnetic flux, electric field, other things, and charge, displacement, sigma, all those type of things, how they are related. For example, D. Normally, D definition is a displacement vector. It is useful when you are using a material medium. If it is free space, it has no use as such. Okay, you don't need to use that. But if it is a material medium, just to differentiate one material to another material, we use this D. Okay, so that is actually, we can define like this. Normally it is defined, it is dependent on electric field. If it is free space, we define D is like that. Epsilon 0 is what? Epsilon 0 is?
Permittivity, sir.
Permittivity. What is the value you know in free space?
8.854 to 12.
10 to the power minus 12?
Yes, sir.
What?
Farad per centimeter.
Really?
Farad per meter.
If minus 12, it is farad per meter. Okay. This is free space. So because this is a fundamental constant, so in free space, you normally don't need to introduce additional D. Just it's a scaling of electric field. Okay. But if it is a material medium, you know, if there is an electric field, that electric field in the material medium can create some kind of dipoles. Dipole moments will be created. because electric field can apply some force on charge electron on the material. So if it is applying force on electron as well as core nucleus, so they will be actually displaced differently, because core nucleus may not be possible to be displaced from its original position, but electron loosely tight and lighter, that can be displaced. So when this electron surrounding the nucleus is a bit displaced, then you can think of some kind of dipole creation. So that dipole actually can create also electric field surrounding it. So that electric field you have to count for your Maxwell's equation. Okay, if you are just combining all these equations, that additional field, this additional field can be a different direction. This whatever polarization is being created, dipoles are created, that can give you electric field. That means that will create electric field surrounding it in different direction. That means you have an external electric field, and then you have internal electric field that is a bit of distorted. So what you can get, that you have inside the material medium, you see the resultant. So to incorporate that resultant, we use this polarization. That means dipole moment per unit volume, because all these we are talking per unit volume, right? Normalized with a material per unit volume. So that is one material, we call it as a material property. So together with these 4 equations, this is another one equation which we must not forget whenever we are designing waveguide or light matter interaction, etc. What is this P? Basically, we simplify that one, epsilon 0 E plus epsilon 0. We introduce one additional parameter which is actually depends on material, and we write like this. That is also proportional to electric field. Whatever it is, P is there, that can be proportional to electric field with additional constant that comes from the material property. Okay, and this can be written as epsilon 0 1 plus, and it is called susceptibility, chi E, susceptibility E. And this 1 plus chi E actually we consider as a we consider that as a what? So we have written there D equal to epsilon 0 E plus P, and that can be written as epsilon 0 E plus epsilon 0 chi E E, right? And then we can write this one as a epsilon 0 1 plus chi E E. That is material property. Material property because of the electric field. Epsilon 0, we write that one as a epsilon R E, and that we simply write as a epsilon. Okay, so this is very important. This 1 plus chi E, that is susceptible material property, that we are considering as a relative dielectric constant, epsilon R. So, and epsilon R multiplied by epsilon 0, that is called actually, that is permittivity of the material. Okay, so permittivity of the material we can just consider. But thing is that that's material actually, whenever you are considering this electric field is a vector quantity. So anything you multiply, that can be a scalar and that can be a tensor also. That means different direction electric field can interact with the material differently. So this additional term chi E, that can be a tensor, that epsilon can be a tensor. Okay, so vector multiplied by tensor, you can get a vector also, D, displacement vector. That is actually how electric field, and you, whenever it is in the material medium, then how to deal with that total thing into your Maxwell's equation that comes with the D. Actually, you know, if you just go back to previous 4 equations, all are first one known as Faraday equation, second one Ampere's equation, and last 2 Gauss equation. But Maxwell's introduction is this del D del T, that part. And because of that introduction, he actually revolutionized everything for the electromagnetic theory. Only that introduction. And then all these four together is later came to becomes popular as Maxwell's equation. Just introduction, only one thing, that is actually D in the all these four equations. Okay, so this is your permittivity, and here we are saying that this can be tensor, and sometimes what happens, this also this material property may not be as linear as we are expressing like this. That electric field will not be, whenever you are increasing the electric field strength, then the equation may not be like this. That means this P, if you are just considering that is actually your electric field and this is your polarization, it may not happen that always polarization is proportional to electric field in the material medium. It can go like this. Little bit it can bend also. So in that case, we can actually expand this second term in Taylor series around a particular electric field. If I want to define what is the polarization, then I can just define how much stretch, how much we are considering. That may be not linear. So in that case, we can expand this in a Taylor series. So in that case, that nonlinearity we can include, and that nonlinearity also you can incorporate in your Maxwell's equation to see the effect, ultimate effect. And that is very, very important for quantum photonic applications. We will be discussing later, that nonlinearity. Okay, so and another one thing, similarly, similar to D, we have another equation, material equation, that is actually B equal to so-called mu 0 magnetic field plus mu 0 M, that is magnetic moment per unit volume. Okay, that can be considered as a mu 0 H plus mu 0 susceptibility, magnetic susceptibility H, and that can be considered as a mu 0 1 plus chi m H, and that can be considered as a mu 0 mu r H, of course vector, and that can be considered as a mu H. So that is actually so-called permeability. Okay, here also you can see some nonlinearity, etc. So, but normally most of the material, dielectric material, they are non-magnetic. Non-magnetic means this mu r equal to 1. So we consider mu r equal to 1 when any optical material we use, most of the time they are non-magnetic. So we will not bother much about this mu r. We'll be just dealing just simply mu 0. And mu 0 value, you know. What is the mu 0 value? Anyone? 4 pi into 10 to the power?
-7.
Minus 7. And?
Henry per meter.
Huh?
Henry per meter.
Henry per meter, right. Henry per meter. Henry per meter. So these are the fundamental constant we can use, and for optical domain, whenever we are considering, we will not bother much about mu r. That is simply we will be considering 1. But epsilon r, when it is nonlinear medium, etc., that can be tensor, that can be nonlinear, all these things will be included, and then we can see the response of electromagnetic wave inside the material medium. And because of that, actually, we can design different type of functions, for including modulator, including your quantum photonics components, all those type of things will be coming into picture. And also, we can, even if it is a laser active medium or diode, laser diode, etc., there also will come to discuss about this chi, how it is modified. Susceptibility, how it is modified for gain medium, for observing medium, all those type of things included here, and all those things we need for our discussion. So you can now understand why I am stressing again and again, you need to go through your knowledge of Maxwell's equation and plane wave, etc. That will be very useful. I stop here. Yeah. Thank you very much.